Registrazione. Ok, vai Nicola.
Bene, benvenuti al terzo dei Complex Analysis Seminars. Prima di introdurre lo speaker, prego tutti di spegnere il microfono e anche la videocamera, a meno che non vogliate intervenire, per evitare ritorni di cose del genere. Speaker oggi è Nikolaos Chalmoukis, Università di Bologna, che parla di Random Interpolating Sequences for the Dirichlet Space. Okay, Nikos.
Thank you, Nicola. Hi to everyone. Good afternoon. Okay, now you should be able to see. Can you see the shared screen?
Yes.
Yeah.
Very good. So I'm going to talk about random interpolating sequences in Dirichlet type spaces, mostly in one variable. And because, okay, just for mainly for my convenience, I want to give an outline of the talk so I don't get lost. I think there are too many ways to introduce and talk about these problems. I mean, one is the historical approach, and the other one is the abstract modern approach. This time I choose the second one because I think it incorporates more problems at once. Although at times I will be unfair to the people that did the first results and so on. So I'm going to, in the first part, I'm going to talk about interpolation in reproducing kernel Hilbert spaces, mostly in the disk, but it can be easily generalized to any domain actually, and their multiplier algebras. Then I want to say some results from the literature, and then I will discuss how to randomize these kind of questions. There are at least a couple of ways. I'm going to mainly focus on the first one, and I will give also some results that we had and so on. So let's start by the very basics. We have a reproducing kernel Hilbert space. So that is a space of functions on some domain. Here, usually my domain is the unit disk, and that it has a reproducing kernel. So that's a function of two variables. Okay, what happened? One node just restarted for some reason.
Yeah, we lost the sharing. I think you have to reshare the video.
Yes, I hope this does not happen too often. Okay, yeah. So if restricted to the one variable, then the kernel K just reproduces the value functions in the space through the inner product in the Hilbert space. So the examples that, I mean, you can keep in mind for the rest of the talk and will be relevant is mostly this family of, and you can say Hardy-Sobolev spaces in one variable. So you introduce a parameter s greater or equal than -1, and then you define this weighted L2 norm on the Taylor coefficients. So an are the Taylor coefficients of the power series of f in the disk. And I mean, this family of reproducing kernels reproducing kernel Hilbert spaces contains most of the important examples that we have. So for s equals 1 is the Bergman space. For s equals 0 is the Hardy space, of course. And for s equals -1 is the Dirichlet space. And you can even calculate explicitly the reproducing kernel, which is given by this expression if s is not equal to -1, and by the logarithm as it is to be expected in the Dirichlet space. So a little more about the multiplier algebras of this space. So you can define the multipliers of a reproducing kernel Hilbert space as the functions, any function actually, such that if you multiply pointwise, this is multiplication in the pointwise sense, remains in the reproducing kernel Hilbert space H for every f in H. And okay, closed graph theorem, very standard, gives you that. Okay. For some reason, I cannot. Okay, here it is. The closed graph theorem gives you that the operator that induces a multiplier which sends f to mf is a bounded linear operator. Some other remarks is that if the constant function is in the space, then of course the multipliers are contained in the space by the definition, because you have to multiply one and remain in the space. And another interesting fact, which is not trivially obvious, but you can do it pretty easily, is that the multipliers are bounded analytic functions. And for example, in the Hardy case, it's exactly the bounded analytic functions. So we have one inclusion. The other one is simply if you write the norm of m times f in the Hardy space, then you can dominate by the H infinity norm of mu times the I don't know why it's doing this, but it's not very okay. So yes, what I was saying is that you can dominate this by the H infinity norm of m squared.
Because we cannot see your screen.
You cannot see. Okay. Okay, I'm sorry about this. I'm not sure. Okay. Yes. And I was saying that yes, you can see that any bounded analytic function is a multiplier for the Hardy space, just because you can dominate the norm of m times f pointwise like this. So let's talk a little bit about interpolation itself. Interpolation has, I mean, you can say it's the study of restriction operators. What is a restriction operator is, can you see like this, or maybe I can enlarge it? Okay, a restriction operator is an operator. So you take a sequence of a discrete sequence in the unit disk, and then you have an associated restriction operator, which it can act on the multiplier algebra, and what it does is just restricting m on its values at zi. Okay, so notice that from our observation before, this is always a well-defined operator because multipliers are bounded analytic functions. So you are certain that you end up in L infinity. And you can do a similar thing for the Hilbert space itself. But I mean, it's not clear. It turns out that the best that you can do is to define a weighted restriction operator and weight by the norm of the reproducing kernel. And why I have a dust arrow here is because if you do not put any extra hypothesis in the sequence Zi, then maybe it might very, very well be that TZ is not everywhere defined. So it might be that there are functions that if you restrict them, then this weighted sequence is not in L2. Okay, so a priori, this is only defined on a subspace of the reproducing kernel Hilbert space, but it's fine for us. And now you have some sensible definitions. So we say that a sequence is is multiplier interpolating, or MI for short, if RZ is surjective. This means simply that for any sequence of bounded data, I can find a multiplier which interpolates the data. So a short way to say this is to say that it is the restriction operator is surjective. And then we go to the operator TZ. And here we have, exactly because we don't know if this is always well defined, we have ambiguity. So we say that is simply interpolating the sequence Zi if the operator is surjective, which is the least you can ask, so that it makes sense to say that the sequence is interpolating. So exactly as before, if for every AI in L2 now, I can find an F such that now, of course, you will have the weight in the game. So you have this, for every AI in L2, I can find an F which solves this interpolation problem. We will say that it is simply interpolating, but in reality, another notion of interpolation is much more used, is to ask also for TZ to be everywhere defined. So if this happens, we say that the sequence is universally interpolating. So this means that it is, by the closed graph theorem, again, it means that it's a bounded linear operator. So we have three notions of interpolation, and let's investigate them a bit closer. Okay. So about what I said before about the boundedness of TZ, if you write down what it means for TZ to be bounded, you end up with an inequality like this. You end up with this inequality. Here, you can see what I'm writing, right?
Yeah, you see.
Okay. So if you ask, boundedness of TZ is exactly this this estimate for every F in the reproducing kernel Hilbert space. And now you can see pretty much by definition that this means that if you have a measure, which is a discrete measure, so you put some Dirac masses at the points of the sequence, and you weigh them by this weight. Then what I'm saying here is just that H is a subset of L2 of this measure, and this is what we call Carlson measure. So the requirement that TZ is bounded can be translated to a Carlson measure condition on the associated measure to the sequence. Let's call this measure the measure associated to the sequence. And another observation. So if we are in simple interpolation, so just that we can solve the interpolation problem for any data, then by the closed graph theorem again, you can find a bounded right inverse to the restriction operator. And what this means is that not only you can solve the interpolation problem for any AI in L2, but also you can solve it in such a way, so you can find such an F, which has a norm in H. Okay, so here is the norm in H, is bounded by the L2 norm of the sequence. Okay, I think that's clear, right? Because if you start with A in L2, then your F is just this. This right inverse of TZ of the sequence A. And you get immediately by the property that it's a right inverse to the restriction operator, that it solves the interpolation problem. And by the fact that it's bounded, you get that you have this norm estimate. And now I should move to another two facts that come out from the definitions. And there are two sufficient conditions. Two necessary conditions for simple interpolation, and hence for universal interpolation. So remember that we asked that we should be able to solve the interpolation problem for any data in L2. So in particular, we can solve it for the standard base in L2. So EJ is just the vector everywhere 0, and just 1 on the jth position. And if we apply our definition and the previous remark that we can solve the problem with a bound on f, we find a sequence of functions fi such that fi at zj is just delta ij. So it's 1 if I is the same as j, and 0 in other cases, and plus times this weight. And of course, we have a uniform bound on fi. So here I would like to mention that this gives, I mean, there is a connection always with interpolation in reproducing kernel Hilbert spaces. There is always a connection with base theory, but here we can see it explicitly, that this requirement is just saying in base theory language that this normalized sequence of reproducing kernels, so KZI normalized by the norm, is uniformly minimal. So uniformly minimal in base theory means, so a sequence in a Hilbert space is uniformly minimal if there exists a coordinate sequence. That means that we have this relationship. So inner products x and inner product ym is delta and m, and that the product of the norms is uniformly bounded. Some C, not infinity. So what we say here is that if your sequence is simply interpolating, then this sequence of normalized kernels must be uniformly minimal. Usually, I didn't write it here, but usually we call such a sequence strongly separated. Because that comes in contrast with a weaker condition, which is called weak separation. So a weaker condition is that for n, and now I just pick pair of points, and I say that I can find a function which is 1 at 1 and 0 at the other, and you have this norm estimate. So this is immediate from what I have above, because if strong separation holds, then I can just take Fij to be Fi, and I'm done. But this is much weaker. Why I insist in this definition is that it is in many cases is much more geometric and easier to understand. So, for example, remember again this space is ds. So this space is that before we defined with this norm. Then so here is S equals 0 is the Hardy space. S equals -1 is the Dirichlet space. So if S is greater than -1, then weak separation is equivalent to just separation in the hyperbolic metric. So if a sequence is weakly separated in these DS spaces, not in the Dirichlet space, all the other spaces in the list, if and only if the hyperbolic distance of 2 points in the sequence is bounded below by some epsilon.
Because, may I ask a question?
Yes, of course.
I thought it was S is equal to 1, the Dirichlet space.
Okay, there are at least 4 ways to define this scale of spaces, but the way I did, I think it's... you're right. Yes, of course. Okay, then let's see. Yes, S equals 1. Okay. I think I messed this up also below, so I will have to correct continuously. So S.
Yeah, you wanted to have some minus S in some place.
Yeah. So I will correct it also below, remind me. But for S strictly less than 1, the separation is just the hyperbolic separation. For S equals 1 in the Dirichlet space, separation is a bit more tricky, but we will see it later. So now for some history. Okay. So okay. So the first, I mean, To be honest, the first paper in the area was probably Pick in 1908, but the first one that falls into these definitions that we have given is probably by Carlson, who characterized the interpolating sequences for the multiplier space of H2 of the Hardy space. And then you have 3 years later, you have Sapiro and Shields, 1961. They give a characterization for simply interpolating and universal interpolating sequences for the Dirichlet, for the Hardy space itself. And the results are quite surprising. And they prove that all definitions are equivalent. Furthermore, they are equivalent to the fact that the sequence is weakly separated. So I remind you that in the Hardy space, this just means hyperbolic separation. And of course that DMZ is a Carlson measure. And we know Carlson measures, thanks to Carlson, for the Hardy space. So this is a characterization that we like. Exactly because it's geometric. You have hyperbolic separation, which probably we understand quite well, geometric thing, and then you have a Carlson measure condition, and we know Carlson measure for the Hardy space. And the Hardy space falls into a class of spaces which have the so-called complete Nemalina peak property. And I mean, it's a quite technical property. I'm not going to explain exactly what it is now, but it's a property that is satisfied by all spaces in the family of for sigma between 0 and 1. Okay, this is the same mistake. But so all spaces that are between the Hardy and the Dirichlet space satisfy this so-called complete Nemalina peak property. And we're going to concentrate on these spaces, and the research in the last years has concentrated a lot on these spaces because the theory is rich and it's quite uniform. So you can prove similar things for all these spaces that fall into this category. So just to give you a hint, if you have not heard whether this property before, maybe you know that this result I said before from Pick, which says that if you are given some finite sequences of points in the unit disk, so these are in the unit disk, then you can find some analytic function from the disk to the disk, which interpolates this points, if and only if this matrix is positive semi-definite. So this is the so-called Pick matrix. This is Pick's theorem. And you can formulate an analogous problem for any reproducing kernel Hilbert space. So you can see here that, so for example, what appears here is the kernel of the Hardy space. So you can formulate a similar thing for any reproducing kernel Hilbert space. And if this equivalence still holds true, we say that the space has the simple Pick property, and then you have a tensor analog of this thing. And if this holds, then we say that it has the complete Nemalina Pick property. So it's probably it will take me half an hour to explain exactly what it is, but I think you can be happy by thinking complete Nemalina Pick property as one of these spaces in this scale between Hardy and Dirichlet. So exactly what I was saying before is that I mean, you have this result in 2017 by Aleman, Hartz, McCarthy, and Richter, which says that if H has the complete Nemalina Pick property, then interpolation in the multiplier space is equivalent to universal interpolation, and it's further equivalent to these two conditions that we saw before. So the Carlson measure condition on the associated measure and the weak separation. This is a fantastic theorem, and Probably I should tell you that it's actually very close connected to the so-called Cadison-Ziegler problem. And in fact, one of its reformulations, the so-called Feichtinger conjecture. Feichtinger conjecture was known to be equivalent to the Cadison-Ziegler problem, and it can be formulated like this. So if you have any sequence in a Hilbert space, which is Bessel sequence, then you can write it as a finite union. So you can split the sequence in a finite union where each of these subsequences, let's say, is a Riesz sequence. So this was a known reformulation of the Cadison-Ziegler problem. And as soon as the Cadison-Ziegler problem was solved, the Feichtinger conjecture was solved, and we were, Aleman, McCarthy, Hartz, and Richter were able to prove this characterization of universal interpolation, universally interpolating sequences in this type of spaces. That's to add to what I was telling you before, that basis theory is closely connected to interpolation. Okay, one thing to notice about this characterization is that it leaves out simply interpolating sequences. So now, at this point, we don't know much about simply interpolating sequences. I personally know only one space which it has simply interpolating sequences which are not universally interpolating. So in the Dirichlet space, we know that there are examples of simply interpolating sequences which are not universally interpolating. So you can solve the interpolation problem, but this weighted restriction operator is not bounded. And but a more concrete characterization of them it's not known even in the special case of the Dirichlet space. Maybe here I can mention in passing a theorem that I had from 2018, which reduces. One way to see it is that it reduces the problem of simple interpolation, always in the case when the associated measure is finite. It reduces the problem of simple interpolation in the Dirichlet space to some kind of simple interpolation in the Sobolev W12 space. So somehow this theorem says that it suffices to be able to interpolate by a non-analytic function, and then you can find analytic interpolating functions. Okay, I'm not going into the exact definition of what simple interpolation is for W12D, because you don't have a restriction operator because functions are not defined on points. So you have to take some small hyperbolic disk around its point and then restrict your function there and so on. But very little is known in general. Even in these DS spaces for S less than 1, we don't know if universal and simple interpolation are equivalent. Okay, so now we can go to random interpolation. We had to at some point because it was in the title. Why to randomize? One answer to is that I mean, you want in some sense to guess which situations are generic, are found often, and which situations are very rare to happen. So if you have a random sequence, you can ask from a probability of being something, interpolating, and so on, and this way understand what is more probable to happen and what is not. And it's not that you can do it only one way. I will concentrate here on what is called Steinhaus random sequences. So you start with some theta n, a sequence of independent uniformly distributed random variables in the 0 to pi interval, which will represent, of course, the argument of our points. And you fix a deterministic sequence of radii. of the points, which you can always assume without loss of generality that it's strictly increasing or simply increasing. And then you define the random variables lambda n to be this fixed radius times the point on the circle, which is determined by this argument. This is a sequence of independent random variables, and it's called the Steinhaus sequence. And now you notice something, that this is a tail event. What it means to be a tail event. A tail event, if you have a sequence of independent random variables, is an event in the sigma algebra that is independent of any finite subset of the random variables. And what I say is that the event of being interpolating in any of the above senses is a tail event, because if I remove a finite number of points from the sequence, so I don't know if this is immediately clear or not, but if a sequence is interpolating or not, it only depends on the tail of the sequence. I mean, I can, if I find the function which interpolates only on these points on the tail, then by adding some polynomial, I can fix the values also here. The problem is the tail. So in fact, interpolation is a tail event. And this means that the Kolmogorov 0-1 theorem applies, which says that the tail event must have a probability of 0 or 1. So there is some condition on the sequence of radii fixed, which tells me if this Steinhaus sequence is interpolating with probability 0, and if this condition is not satisfied, then it's interpolating with probability 1, or the other way. So yeah, and the same applies to any of the above conditions. Again, weak separation, Carlson condition, strong separation, and so on. So we are after this. We are after this laws that determine these laws that come from the Kolmogorov 0-1 theorem. Okay. So I will recall some known results, but okay, first let me introduce this symbol counting function. So I have 0, 1, then I split this interval into halves of halves and so on, and then I count how many points I find in each of these subintervals. So these subintervals, if you see them as a subset of the unit disk, represent points that have pretty much constant hyperbolic distance to the origin. And this counting function nn counts how many points in the sequence have hyperbolic distance pretty much n from the origin in my Steinhaus sequence. And we have some known results. First one is from Kosra 1990, which says that the Steinhaus sequence is almost surely hyperbolically separated, if and only if this condition holds. Notice that here somehow it enters the quadratic of the counting function, which is a bit strange maybe. And then you have Rudovitz, which examines the Carlson condition in the Hardy space. It says that exactly the same condition is sufficient for a sequence to be Carlson. So these theorems together give a characterization of Steinhaus interpolating sequences in the Hardy space. So the Kolmogorov 0-1 law is exactly this one, this quantity to be finite. We had some improvement with, okay, what I'm going to mention from here on is a work from collaborators from Bordeaux, Hartmann, Kelai, and Wick, Brad Wick, and we had an improvement in the theorem of Rudovitz, which says that, I mean, it suffices to replace any 2 by any number bigger than 1, and if this is satisfied, then the Steinhaus sequence satisfies the Carlson condition almost surely. And also, if you put exactly 1, this is not sufficient. If you put exactly 1, what you get is the Blaschi condition, if you notice. Okay, but things get even more interesting, in my opinion, in the scale of Dirichlet spaces. So again, here I have to put a minus s. I think this is the minimal effort way to correct the error. So if s is between 0 and 1/2, then we have this this law of a universal interpolation. So our Steinhaus sequence is universal interpolating, if and only if, again, the same condition. If this is finite, it's with probability 1. If this is 0, then it's almost never universal interpolating. And the same is true if you replace simple interpolation. So we see that in this probabilistic setting, simple and universal interpolation coincide. So in some way, this tells us that simple interpolation is, even though it might happen, we don't know, is not a generic situation. It happens very rarely. But the behavior changes in the, again, minus s. Okay. So this is a strange point in the theory, that we have that the behavior changes completely when you go to the half of the scale of spaces which is closer to the Dirichlet. So here we have a different law. So Steinhaus sequence is universally interpolating with probability 1 if this summability condition now in the sequence happens. So this is minus, same old error again. And here, the nature of the condition is different. First of all, notice that there is no square or power law on the counting function. It's just the summability condition in the sequence. And the same is true again if you replace universal interpolation by simple interpolation. So again, probabilistically, there is no distinction between the two of them. And notice also that this condition is a condition that exists always in the literature. Is a theorem of Carlson, which says that if this is finite, then Zn is a zero sequence for ds. So this is a condition which is sufficient. Is not equivalent to being a zero sequence of Carlson, and it's exactly the condition that we have here. Okay, absolute value, it's really not necessary here. Rn are positive. So the next theorem says exactly this, that in fact, not only universal interpolation and simple interpolation are equivalent, but they probabilistically they are also equivalent to being a zero sequence. One direction is clear by Carlson's theorem. If this is finite, then not only probabilistically, but always this is a zero sequence. But also the other direction is true. That probabilistically zero sequences satisfy this condition, which I remind you is not the condition that satisfies all zero sequences. Zero sequence, I mean, I didn't mention maybe. Zero sequence is a sequence such that I can find a function in my space which vanishes exactly on this sequence, and f is not zero. So we have a completely different behavior on this half of the spectrum. And was there something else I wanted to say? Probably not. Okay. So Dirichlet space. So the Dirichlet space, again, the general theorem which describes universally interpolating sequences is in the same flavor with the one that we had for DES when S was bigger or equal to 1/2. So it's a summability condition in the sequence. So it's universally interpolating if and only if this sum is finite, and it's almost never universally interpolating if this sum is infinite. And again, this is a condition, this time from Shapiro and Shields, which ensures that the sequence is 0 for the Dirichlet space. Yeah, but okay, the result looks the same, right? But it's a bit more bit more tricky, let's say, because separation. Remember, it's a thing is different in the Dirichlet space. So in DS, when S was smaller than 1, separation, weak separation, was just hyperbolic separation. So let's take a look now what is separation, weak separation for S equals 1. It's the following condition. So a sequence is weakly separated in the Dirichlet space sense if I can find an epsilon positive such that the hyperbolic distance of every 2 points in the sequence is bounded below by not only epsilon, but epsilon times the hyperbolic distance of one of the 2 points to the origin. So maybe a picture is helpful to understand this definition. So let's say this is my point Zi. Here is the origin. Here is the boundary of the disk. I have some hyperbolic disk around Zi, which now has radii, hyperbolic radius, epsilon times the hyperbolic distance of dz to the origin. So this segment is hyperbolically comparable. The hyperbolic length of this segment is comparable to the hyperbolic length of this segment from Zi to the origin. And in this disk, there are no other points in the sequence. So if I have another point, it must be somewhere here. That's what the condition. So you understand that it's a much stronger separation condition. And of course, you can ask, is there a characterization of Steinhaus sequences which are hyperbolically separated in this sense? And we have this again theorem for so the Kolmogorov 0-1 law for weak separation in the Dirichlet space for a Steinhaus sequence generated by some radii is given by the condition, this condition. So you count how many points are in a hyperbolic disk within the hyperbolic distance n of the origin. So you have the origin, you have some points here. This is hyperbolic length n, and this must not grow faster than 2 to the gamma n, where gamma is some number smaller than 1/2. So it must grow exponentially slower than 2 to the n, to square root 2 to the n. And so this is if this happens, then is almost surely weakly separated in the sense I mentioned before. If this does not happen, then it's never going to be, almost never going to be weakly separated. So, okay, we have 5 minutes. I have 5 minutes, or I don't know if I'm going to I mean, it's
yes, you have.
Okay. I'm not going to talk about don't worry, I'm not going to talk about the details of the proofs and so on. I just wanted to highlight some techniques that they could be used to solve this problem. So, okay. Yes, so let's concentrate in one statement from the proofs before. So if this condition happens, this Shapiro-Shields condition happens, then we would like to show that almost surely it's weakly separated and Carlson. Okay, that would imply that it is almost surely universal interpolation, universally interpolating, because remember, for every space with a complete Nevalina peak property, universal interpolation is equivalent to weak separation and the Carlson measure condition. Okay. Okay, the weak separation is a geometric argument. Let's. I'm going to concentrate on the fact that universal that this condition implies that the sequence is almost surely Carlson for the Dirichlet space. And for this, we use the characterization of Carlson measures by Stegenga. So what Stegenga says is that if you have a positive measure, then it's Carlson for the Dirichlet space, if and only if it's subcapacitary. What does this mean? Is that I take this EI, this some intervals on the boundary of the unit disk. So this is E1, E2, and I take the corresponding Carlson boxes. And then the mass that I have in the Carlson boxes, so this, the mass of the measure inside here is controlled by a constant times the capacity of the set, which is that's the union of these arcs. Okay. This is generally not easy condition to check because it involves multiple boxes. It's not a one box condition, like in if you know probably in the Hardy space. It's a one box condition. Here you have to check all possible configurations of points. And this is usually quite difficult. Moreover, because it's practically impossible to estimate the capacity for an arbitrary configuration of intervals. So the idea is that, I mean, for a Steinhaus sequence, you don't have to bother with the multiple box condition. If you prove it for one box, then you can make it work. So first, you want to prove it for one box, and you consider a Whitney decomposition of the unit disk in a family of rectangles. So this you decompose the unit disk as usually, and so on, and you have this family of rectangles. And then you define this, so this rectangle, for example, is R alpha, okay. And you define this random variable, which is the measure of the Carlson box corresponding to this rectangle. So for this rectangle here, the Carlson box is everything that lies below, is all this, is the half disk in that case. And you divide this by, because you want to compare it with the capacity, you divide this by the capacity of the interval on the boundary. And you use Borel-Cantelli lemma to prove that this is almost surely bounded. Here it's a bit more technical because I mean the simple-minded estimates do not work very well. So you have to use what is called exponential moments method from probability theory. And you get, with Borel-Cantelli lemma, you get the one box condition. So you get this capacitary estimate, but only when n equals 1. But then you can extrapolate from this the whole condition because of symmetry. Because of symmetry of the Steinhaus sequences, so that the fact that they are uniform, the argument is uniformly distributed, and because of the symmetrization inequalities for capacity. So what you do is that you start with now any collection of intervals, and you just notice that this is a very simple calculation, very intuitive, that they have the same distribution as the mass on the intervals that have the same length. So EJ prime has the same length with EJ, but EJ prime are adjacent. So you start from a situation like this, and now you move to a situation like this, actually without losing anything, because the distribution of this random variable is exactly the same as the distribution of this random variable. And then, pretty much that's the trick, because okay, the mass that you have here is less. Okay, so you want to sum the mass here and the mass here, but you just take the biggest Carlson box, which is the Carlson box corresponding to the union of the intervals, and this dominates the previous one. You have proved the one box condition, so you know that almost surely this is controlled by the capacity of the union. And this comes the symmetrization inequality for the capacity, which says that the minimal capacity is attained if the intervals are adjacent. So you can dominate, you have the free bound above by moving back to the original EJ intervals, and you are done. Okay, so I hope it was not very. It was understandable. That was pretty much that I had to say. Thank you very much.
Thank you. Are there questions for Nikos? Remarks? I have a question.
Yes.
It's the Hardy space on the unit ball in CN. I mean,
Yes.
that's a mystery, right? The interpolating sequences. Actually, it's a Bordeaux mystery because Eric Amara worked on it for many years.
I think there is a characterization of Steinhaus. I mean, you can define Steinhaus sequences, obviously, and I think there is a characterization of weak separation in the Hardy space. But then this does not give you the full story, because as far as I know, you don't even know if weak separation plus the Carlson measure condition gives you the interpolation. So
right. That's a mystery, but in the random case, it's a...
we have not looked into this, but I don't think it would be very easy without knowing more in the deterministic case.
Dirichlet space in more dimensions, that's...
Dirichlet space, probably you can do something because, I mean, exactly because you know that weak separation plus the Carlson measure condition are sufficient. So probably you can do something. Although these symmetrization arguments, I don't know if they are easy to transfer in the sphere of CN, because I mean symmetries are more difficult. I don't know if you have this capacitor inequality
in higher dimensions.
So somehow for a set of fixed measure, if you know which configuration gives you the least capacity, I guess it's not a trivial problem.
Okay, but take note. Are there other questions? Remarks? Okay. Well, let's thank Nikos again.
Thank you.
Okay, next talk will be next week at the same time.